Hello, welcome to another video. So today I'm going to talk about Stefan-Maxwell equations. And Stefan-Maxwell equations are used to look at binary data, binary mass transfer data, and we can extrapolate information from that to apply it to multi-component mixtures. So looking at this equation, we have the xi. These are like in the last video, this is going to be the mole fraction of component I or component 1 of the two components in this mass transfer equation. Then the next term is this upside down triangle with mu I. So this is going to be, the upside down triangle is just a gradient, and in the past videos also we talked about how a gradient is just the driving force for in this case mass transfer. So the gradient of mu I, mu is just the chemical potential, so this is so the driving force here is this chemical potential gradient. Then we have Dij, and this was in the most recent, like the previous video, we said that D is going to be the diffusion coefficient. And that was, we found that when we looked at Fick's law. And then specifically, the Ij is just saying that this is how species I diffuses in species J. There we go. And then we have these ends. So this is going to be molar flux. And then this is of component J and component I. We also have C, which is the concentration. Or rather, we can say it's the molar concentration, to be more specific. And then R is still ideal gas constant, and T is still temperature. So now we can, I'll just rewrite this to make it a little bit more simple. So on this side, we said that this term here, the chemical potential gradient, that was going to be the driving force for this mass transfer. So we are going to just simplify it and say that the driving force is going to be Di, or of component I. And then the right side we're going to keep the same. It's going to be equal to the sum of the mole fraction of I times the molar flux of J minus the mole fraction of J times the molar flux of I, all over the molar concentration times the diffusion coefficient of species I and J. So now that we have this simplified version, I'm also going to write out the other Maxwell equation that relates the components by their velocities. So that's going to be that, I'll just do this. So first, I'm going to actually change these x's here, like the mole fractions. I'm going to change the variable from an x and change it to a y instead, because we're going to be looking at this as a vapor instead of a liquid. So the x's represent the mole fraction of a liquid, the y's represent the mole fraction of a vapor. So I just changed those, but their whole equation is still the same, it still means the same thing. And then if we're looking at this in terms of velocity, the equation is going to still be that the driving force is going to be equal to the sum from j equal to 1 to n. But this time it's going to be that the mole fraction of I times the mole fraction of j times the velocity of component j minus the velocity of component I is all going to be over the diffusion coefficient of ij. So now if we're trying to find a way to relate these two equations together, then we want to find like what's different between them, and we can see that the obvious one is the concentration being in the first equation and not in the second. So let's multiply concentration by the numerator and denominator, that way it's in this equation here. So that's going to look like still the driving force still is equal to the sum of, we're going to multiply the concentration by the numerator and denominator. So we have the concentration times mole fraction of I times mole fraction of j times the velocity of component j minus the velocity of component I. It's going to be over the concentration times the diffusion coefficient of ij. So now if we multiply this out, we're going to have the driving force I is equal to the sum from j equal to 1 to n. This is going to be the overall concentration times the mole fraction of I times the mole fraction of j times the velocity of j minus the overall concentration of mole fraction of I, mole fraction of j, velocity of I, all over all over the overall concentration of the diffusion coefficient of I and j. Great. And over here, I'm going to make a note that the overall concentration times a mole fraction, this can be of I or j, whichever one, is going to be equal to the concentration of that species of I or j. So this equation here can finally be rewritten. Driving force is equal to the sum of j equal to 1 to n. Here we have concentration times the mole fraction of j, and that's going to give us the concentration of j. So it's going to be mole fraction of I, concentration of j, times velocity of j, minus, this is going to be similar on this side, concentration times the mole fraction of I is going to be the concentration of I. So mole fraction of j, concentration of I, velocity of I, all over the overall concentration times the diffusion coefficient of ij. So this is that one. Okay, I'm going to copy down the original equation that we have in terms of molar flux. So Okay, and looking at these two equations, the difference here now is these two terms. The concentration times velocity for the specific component. If we look here, it's going to be equal to the molar flux of each component. So I'll write that down over here as well in this section. That the concentration of J times the velocity of J is going to be equal to the molar flux of J, and then the same thing for I, or species I. Like that. So now that we have this relation, let's look at it in terms of diffusion flux. So from the last video, if you remember, we said that the molar flux of, let's say, species I is going to be equal to the diffusion flux of species I plus the concentration of I times the overall molar flux, right? And if we look back right here, not that one, sorry. If we look back right here, actually, we can substitute this concentration out. So we have the molar flux of I is equal to the diffusion flux of I, plus we said that the concentration of I is equal to the overall concentration times the mole fraction of I times the overall molar flux. So now, knowing this, we have molar flux of I, and we're going to do the same thing for J. We can plug that in here to our molar flux Stefan-Maxwell equation. So let's do that. We have, again, driving force is equal to the summation. This is going to be the molar flux, no it's not, the mole fraction of I times, we said that, and J, the molar flux of J is going to be the diffusion flux of J plus the overall concentration times the mole fraction of I times the overall molar flux. And we're gonna subtract the mole fraction of J times the diffusion flux of I plus overall concentration of, over here that's a J. Overall concentration times the mole fraction of I times molar flux, overall molar flux, divided by overall concentration times diffusion coefficient of Ij. Okay, great. So now let's multiply across here. Driving force is equal to the summation of, this is going to be mole fraction of I, diffusion flux of J, plus mole fraction of I times the concentration times mole fraction of J times the overall molar flux minus the mole fraction of J times the diffusion flux of I minus mole fraction of J times the overall concentration times the mole fraction I times the overall molar flux. Again, all divided by concentration times the diffusion coefficient of Ij. Okay. And then once again, we can simplify this. So this term and this term is the same. So you have the driving force equal to the summation. This is going to be mole fraction of I times the diffusive flux of J minus mole fraction of J times diffusive flux of I all over the overall concentration times the diffusive coefficient of Ij. There we go. So this is the Stefan-Maxwell equation in terms of diffusive flux. And we did that again by using the Stefan-Maxwell equation for molar flux, and in terms of velocity, we are able to relate these Stefan-Maxwell equations to each other and get these three different equations from it. It's 1, 2, and 3. So now I'm going to talk about what happens in ideal mixtures with a reference chemical potential in a pure state. So to do that, I'm just going to copy down the original equation that we have here. Okay, here we go. Cool. So here's the equation, and again, we're talking about the chemical potential at a pure state, and this is in an ideal mixture. So that means that the chemical potential of component I is going to be equal to chemical potential of component I at the reference state or at standard state. So that's going to be a circle up there. And then normally these two are not equal, so we have to be able to account for that difference. So for this, we're going to have that the chemical potential of species I is going to be equal to the chemical potential of species I standard state, plus, we said this is an ideal gas, so we're going to have the ideal gas constant times temperature times the natural log of the mole fraction of species I. And this, like I said, it just accounts for the difference that's normally between these two terms. So we want to be able to put this into the Stefan-Maxwell equation. So up here we have that the gradient, the chemical potential gradient, is going to be equal to the change in chemical potential over the change in position. So we're going to plug this part in here and take the derivative. It's going to be d of the chemical potential I standard state plus ideal gas constant times temperature times natural log of the mole fraction of I over dz. And we can take the derivative. So this derivative is going to be ideal gas constant times temperature times 1 over mole fraction of I. It's going to be dxi over dz. And then we said this is equal to the chemical potential gradient. So we're going to plug this in here, and I will rewrite that. So this was the mole fraction of I times ideal gas constant times temperature times 1 over the mole fraction of I dx dz all over ideal gas constant times temperature. is equal to the sum of the mole fraction of I times the molar flux of J minus the mole fraction of J times the molar flux of I, all over the concentration times diffusion coefficient of Ij. So then now if we simplify this, this cancels, we are going to be left with, I'll just copy this down actually. We're left with the derivative of the mole fraction of I with respect to position is going to be equal to the right side of our Stefan-Maxwell equation. So that means that this left side here, this term, when the chemical potential is equal to the chemical potential at standard state, the driving force is just going to be the derivative of the mole fraction of I over, or with respect to position. So now we're going to see how we can break this back down into Fick's law. So when we think about Fick's law, it's going to be in terms of the diffusion flux. So I'm going to use that Stefan-Maxwell equation to start off. Let me scroll up here and I'll copy this down. Okay. Because we want it to be in terms of diffusion flux. There we go. Okay, so to do this, we're going to start out and say that I is going to be equal to 1. So with this equation, if we plug in 1 for I and start the summation, with J is equal to 1, we're going to have that driving force is equal to the mole fraction of 1 times the diffusion flux of 1 minus the mole fraction of 1 times the diffusion flux of 1, over the concentration times the diffusion coefficient of 1, plus, this is a binary mixture, so we're only going to go up to 2 for the summation. So that's going to be plus the mole fraction of 1 times the diffusion flux of 2 minus the mole fraction of 2 times the diffusion flux of 1 over the concentration times the diffusion coefficient of 1, 2. And if you notice, this first term here, this cancels out to 0 because y1j1 minus y1j1 is 0. So there we go. And then we just said, sorry, this should be just 1, not I. So then we just said a second ago that the driving force is equal to the derivative of the mole fraction of I with respect to position. So we can write that in right here. We're going to have the derivative of the mole fraction of 1 over, or with respect to position, is going to be equal to that term there, that the mole fraction of 1 times the diffusion flux of 2 minus mole fraction of 2 times the diffusion flux of 1 is going to be over the concentration times the diffusion coefficient of 1 through 2. So now, if we want to simplify this here, we need to know that the mole fraction of 1 plus the mole fraction of 2 is equal to 1, and the molar flux of 1 plus the molar flux of 2, or rather the molar diffusion fluxes of 1 and 2 are going to add up to be 0. So then this leaves that the molar diffusive flux of 1 is going to be equal to negative molar diffusion flux of 2. So now let's use that to simplify this a bit. And then why would you need to know this? Well, this is because this is where I is equal to 1. So we want all these to be 1s. And as a matter of fact, that should be a 1 as well. Okay, so we're going to use what we got, or what we know in this information here, to substitute out these values with a 2 in them to make them in terms of 1. So first of all, let's multiply this denominator over. So we're going to have that the concentration times the diffusion coefficient of 1 through 2 times the derivative of the mole fraction of 1 with respect to position going to be equal to the mole fraction of 1. We have that the diffusive flux of 2 is going to be equal to negative 1 because this is the same thing. There we go. So because that's going to be a negative out front just to make things easier. Molar flux of 1. Okay, great. Minus, okay, we have y2. So from here, y2 is going to be equal to 1 minus y1. So let's plug that in. For y2, so that's going to be 1 minus the mole fraction of component 1 times the diffusive molar flux of 1, and we can multiply that. It's going to be equal to negative mole fraction of 1 times the molar diffusion flux of 1 minus molar diffusive flux of 1 plus mole fraction of 1 times the diffusion flux of 1, and this cancels and so does this. And if we multiply this negative over, you won't believe what we get. It's the molar diffusion flux of 1 is going to be equal to the negative concentration of the diffusion, times the diffusion coefficient of 1, 2 times the derivative of the mole fraction of 1 over with respect to position. And oh wow, this is Fick's law. That's crazy how we got here, but here we go. That's how we can get Fick's law from the Stefan-Maxwell equation. And then, like I said earlier, why this matters, or why we want to know about Stefan-Maxwell equations, is because it allows us to get information about like multi-component mixtures. So if we have allows the Stefan-Maxwell relations allow us to look at a binary component mass transfer, and we're able to get information from those two components and apply it to the rest of the components within the mixture.